as a consequence of these ideas in the magnetic force, we'll take a look at the case where one can produce circular orbits of a charge moving in a uniform magnetic field. And again, I'll have the same sort of setup. Again, just so I can draw the figure, I'm going to assume we've got a positive charge here, has an initial velocity v upward. Magnetic field is coming out of the page at me, so these are the magnetic field lines coming up. And we assume a uniform magnetic field, and we know the velocity of the uniform magnetic field. It can only deflect the particle. In this case, it will deflect it toward the right, and but it cannot change the speed. And so, first thing I would probably do is calculate the magnitude of the magnetic force on the particle. And I think you can see I'm assuming this V is in the plane of the paper and that B is perpendicular coming out at us for the magnetic field. So the magnitude of the magnetic force is the magnitude of this. The magnitude of Q, I'll just use Q for the magnitude of it since it's a positive one anyway, times the magnitude of B naught, times the sine of the angle between V and B naught. And V is in the plane of the paper, B is coming out at us, and so that angle is 90 degrees. And so the magnitude of the force is QVB naught. And the interesting thing here is Q doesn't change. We've already established that a uniform magnetic field can't change the speed of the particle, and that's the magnitude of the velocity or the speed, and then B naught is uniform. So the magnitude of the force doesn't change for this particle as it moves through its motion. However, its direction does. And if I use the right-hand rule, V going upward, B coming out at us, for a positive charge, it's going to be in this direction when I'm down here. Now the particle will move a distance around. You can check it at every point here, but at any given point, it's going to be tangential to this circle. The speed doesn't change. The direction has changed. Say it's up here at the top. And B is coming out, but if you check again the direction, V cross B again is in this direction. And as you go around, everywhere you go, I have a constant force, Q V naught B, and they're all directed directly toward the center of this circle. So the motion that it undergoes is a case of centripetal under a centripetal force. So the force is always directed toward the center, and we would call that a centripetal force. It's always directed toward the center. The way I always remember this, centripetal is a P here. The force is pushing the object toward the center of the circle. So sometimes you'll hear people talk about centrifugal force with an F here, and to me, I remember that it's fleeing the surface, or fleeing the center, so it's going away from the center. Well, a centripetal force that's constant produces a circular motion, and in fact, we can compute the acceleration from F equals ma, and you find that the acceleration, if the force is constant, then the magnitude of the acceleration is constant. And if you look up here, constant force, F equals ma, so the magnitude of the acceleration is constant. And acceleration always points in the direction of the net force, which is always in the same direction. Now, it's a different magnitude, maybe, so I could also draw the accelerations all the way around here. But again, the acceleration is always toward the center, and so we've got a case of centripetal acceleration. Moreover, F equals ma, and so if the force is constant, divide that by m, which is constant, and you find that it has a constant acceleration always toward the center. So we're satisfying all the criteria for uniform circular motion of this particle as it goes around. And we know tons of things about the uniform acceleration, right? I know that the acceleration, they probably wrote it as A sub c, just to remind you it's centripetal. Uh, it's really just A in this special case of uniform circular motion. Is just the speed squared divided by the radius of the circle it's moving in. And you can use F equals ma. I know the force magnitude, we just calculated that, it was qv b naught. Mass, and then the acceleration, well, it's a centripetal acceleration, v squared over r. So F equals ma gives this equation. I can, well, one of the v's will cancel. I can solve this for the velocity. So if I know q, m, b naught, and measure the radius, then I can get the velocity. Or alternatively, if I know the velocity, the speed it's moving, then I can solve this for r. It's just simply going to be m times v. Here I put a naught on it because it is constant, divided by q b naught. So depending on what you know, you might find the velocity, or you might find the radius of the circle that it moves in. Now, for uniform circular motion, you know that there were several different quantities that were defined, and one of them was the period. And if you remember from last semester, the period of uniform circular motion is the time for one complete trip around the circle, or one complete orbit. And we can use that. The velocity, if you come up here, look at the velocity, q's constant, m's constant, b naught's constant. It's moving in a circle that has constant r. And so velocity, or speed, is the distance moved divided by the time it takes. Well, it moves all the way around the circle, so our circumference is 2 pi r in the time capital T, 1 period. And then usually you solve this for the period. So this equation, I can solve it for the period. I get 2 pi r over v from the equation above. And now then, I know that from above, v is qb q over m b naught r. And so I'll use that expression, q b naught over m times r, to eliminate v. And then kind of a miraculous thing occurs, and we'll talk about that some more a little later. But the r's cancel. And one gets that the period is 2 pi q over m b naught. And that's probably about as good a way to write it as any. Some other auxiliary expressions are the frequency. Frequency, if you remember, is 1 over the period, just by definition. And if I've got the period, then I just take the reciprocal of it, put this down for the period, and the denominator here will flip over on top, and so I get 1 over 2 pi q b naught over m. And so the frequency, the time for one complete well, the period is the time for one complete oscillation or one complete orbit, and this tells you how often the particle makes it around that trip, the frequency with which it makes the trips. It makes one per period. Well, that is sometimes given the symbol F sub c. I don't know if your book does or not. And that is given a name. It's going in a circle, and a circle is a cyclotron. And so this 1 over 2 pi q b naught m is sometimes called the cyclotron frequency. Oh, some other quantities that you've seen before from first semester. The angular frequency, remember, was 2 pi radians times the usual frequency. That was defined to be the angular frequency. And then if this is the cyclotron frequency, I just substituted in our previous expression for the cyclotron frequency, and the 2 pi's cancel, and you get the the cyclotron angular frequency is just Q B naught over M. That's really the one that I usually remember it in because I never remember whether it's 2 pi or 1 over 2 pi. You have to be a little bit careful because some people will, let's go down just a tad, uh, they will, this is truly the cyclotron frequency, but sometimes people get a little sloppy and they know what they're talking about. And they really should say cyclotron angular frequency for this one. They differ by this factor of 2 pi, but sometimes people get a little sloppy in their language and they will call this the cyclotron frequency as well. And I may do it as we get later on. What I claim is that this is really pretty surprising results. If you look at the time it takes to go around, there's a good expression for it, maybe right here, the r's canceled out. So there's no radius dependency on the period that it takes to make one complete circular orbit. And what that implies then is this. If I fire two particles, particle 1 and particle 2, identical in all respects, I'll fire them straight up. The only thing that's different about them, I will fire one of them with a lower velocity, I call that one v1, and I fire another one, particle 2, with a higher speed in the same direction. And if you look at these, go up here somewhere. Here, the radius is related to the speed. M's constant, Q's constant, same particle, same charge, same field. So the higher the speed, the bigger the radius. And so what I know is this. For the low velocity particle, it's going to have a smaller radius, r1. The high velocity, the radius is proportional to the speed of the particle, so it'll have a larger radius, r2. However, in this process, the period, the r's canceled out, and so both of them have exactly the same period. And in that regard, it says that while the one particle is going around this circle, the other particle is going around this circle, and if you fire them at the same instant, they will arrive back at where they started at the exact same time. The period t is the same for both. The only thing that's different is v2 is bigger than v1, and so the radiuses are bigger. Well, and it's just enough, it goes just fast enough so that it goes through this bigger radius, it travels a further distance, but it travels it in exactly the same time as the lower velocity particle does because it travels a lesser distance through this radius r1. Well, kind of a surprising result when looked at in a certain way anyway.